So welcome to today's CDY session, and it's really a great pleasure to introduce Dmitry Khangulyan, who is currently at the Institute of High Energy Physics, Chinese Academy of Sciences, and the Tianfu Cosmic Ray Research Center. And the title of today's talk is Acceleration, Radiation, and Transport of Relativistic Particles in the Jets of SS433. And we're really grateful that Dmitry was able to step in on short notice. Summer's talk had to be rescheduled. It's going to be next spring. So quick introduction. Dmitry got his PhD from Moscow Engineering and Physics Institute in theoretical physics. And then subsequently, he was a postdoc in high energy astrophysics theory at MPIK Heidelberg, and a research fellow also in high energy astrophysics at Japan Aerospace Exploration Agency, and then associate professor in physics at Rikyo University. And he's an expert. He's working currently on LASSO and GRAMS, among other projects. And he's an expert on several topics, as you know, in high energy astro. Most recently, he has done some work on non-thermal emission from microquasar jets, TeV afterglows, particle accelerations in jets, and many other topics. So we are recording this for our YouTube archive. Please mute yourself if you're not speaking. We will have 50 minutes of talks followed by general discussions. And I think we should just welcome Dmitry, and please share your screen and let's get started.
Thank you very much. It's my great pleasure to talk. Let me share my screen. And I hope now you can see my slides. And in this talk, I will so as Reshmi explained, so I'm substituting Samar, and of course I cannot replace her, and especially then talking about X-ray emission. Still, I'm here, and I will talk mostly about study of jets in SS433, which collaborators of mine did in X-ray band. So this study is based on Chandra observation of the Western jet and XMM Newton observation of the Eastern jet. And the talk will be based on these three papers. The first one is by Takira Sudo, where he introduced a simple transport model which allows to describe the distribution of non-thermal emission across the jet sources. And then I will introduce the findings from two observational papers. Both papers were led by Kayama-san, and one was published in 2022. And in this paper, we considered Western jet. And the second paper is now submitted to a journal, to PASS. And in this paper, we consider study Eastern jet, and I hope it will be accepted very soon. And before going into detail, let me remind you some basic properties of SS433, and I will look at this source at different energy bands. And of course, there were several seminars specifically devoted to this source. Still, I think a short reminder might be useful. So here you can see some results obtained in the radio band from this source, and in particular you can, in the left part of the slide, you can see the helical jet which was resolved with radio observations, and this image has a characteristic scale of several arc seconds, and this corresponds at the source distance of 5.5 kiloparsec to approximately 3 × 10⁻³ parsecs. This is still a very large distance compared to the characteristic binary scale, but if we zoom out and look at the larger view, we can see this kind of nebula which spans across approximately 100 parsecs. So this we dealing with a source which kind of covers several orders of magnitude on scale change, and apparently it keeps certain coherency because the orientation of this inner jet perfectly coincides with the orientation of the jet on a larger scale. And actually study of the jet on the small scale is essential for our understanding of this source, because in particular by looking at the jet on the smaller scale, we can measure its bulk speed, and we also can estimate the mass loss rate of the system, and at the end we can estimate the kinetic luminosity of this jet. And in this bigger plot, you can see not only the radio data, which are shown with red color, but also the data obtained at higher frequencies, including optical and X-ray observations. If we look at the source in X-rays, actually it was this source was detected in X-ray long time ago, like 30 years ago. It was already, we could see these kind of excellent morphological maps of the X-ray emission, and from looking at even at this ROSAT quite historical, let's say, map, we can see that the X-ray data suggests that the source is not really continuous. So there is bright central path, and then the rebrightening of the jets, large-scale jets, occur at certain distance. And if we kind of look at this scale, that the 1 degree scale corresponds to approximately 100 parsec, we can see that this brightening approximately occurs at 10 order of magnitude, like several tens of parsecs from the central object. And also the central object is surrounded by a faint region from which no significant emission is coming. This may on the first glance look as a kind of puzzling feature, but in fact it's probably something very natural, because then we are dealing with outflows which propagates to many orders of magnitude in scale as this jet in SS433. We expect significant adiabatic cooling of the flow. So, well, eventually at a certain distance, the jet plasma becomes cold and does not produce an intense emission. And if we look at the comparison of more recent X-ray data, for example, here you can see this composite plot again from the same plot which I have already shown from Samar's paper. We can see that we really see consistent picture with different instruments, and these kind of bright X-ray jets are real. And the next point which I would like to mention is observation of this system in the GV band. And here you can see intensity maps from two different papers, one by Jian Li and another by Ke Fang. And so they originate more or less from the same time, but still we can see a certain discrepancy in the results. So, and in particular, this concerns morphology, and also it concerns the variability properties of the emission, because in the paper by Jian Li, one claimed existence of kind of precession phase variability, and here you can see the obtained light curve and the precession phase, which corresponds to the precession of the inner jet, and here is the GV emission from the source, and this result seems to be very hard to connect to any physical model for the source, because the emission which is detected is coming from much larger scale, and even the cooling time is expected to be very significant. So it's not clear how we may obtain the variability on a scale of several hundreds, or like on a year scale, let's say. And also, if we look at the morphology, Kepang has shown that, well, if one uses together Fermi and Hawk data, then the GV morphology kind of transforms and appears to be consistent with the orientation of the jet, and not kind of offset as obtained by Jian Li, for example. The next important results were obtained in the TV band, and it's started with detection by Hawk in 2018, and that was a very important step, because although one tried to detect TV emission from microquasars, so the many microquasars were observed, the intention apparently was somewhat wrong, because one was looking mostly at the variable emission, which should be generated on the small scales, where and in some cases, for example, we could detect variable GV emission from SIM63 with Fermi, and this emission is apparently produced by inverse compton scattering of relativistic electrons in the jet. There were similar results for signals X1 with similar conclusions. And there was an idea that probably we can also detect the inverse compton emission from the jet on the binary scale, where we have like a massive star which provides dense target. However, the reality was somewhat different, and one first detected the emission, TV emission from large scale jets. And here in the upper left corner, you can see the significance map from the Hawk paper. And after that, well, one realized what is the strategy for observing this type of object, and this system was also detected with HESS. And at the bottom part of the slide, you can see very important results by HESS collaboration, which shows energy-dependent morphology of the TV emission from the jets. And this result is important because of several reasons. Then we're dealing with extended sources in the TV regime. There is always uncertainty with subtracting background or nearby contribution from nearby sources. And with Hawk detection, it was very hard to exclude a hypothetical possibility that these pods, which nicely coincide with the position of the jets, which they still could be a fluctuation. But once has revealed this energy-dependent morphology, it's clear that the TV emission is related to the binary system, to SS433, and somehow it robustly proves the origin of the emission. Another important point is that the energy-dependent morphology implies that this emission is generated by relativistic electrons, because we cannot generate this kind of emission pattern with hadronic scenarios, or at least I don't know how to do that. And on the other hand, with the recent detection with LASO of these sources, there could be still some room for hadronic contribution in this source, and you can see here a kind of spectral modeling which uses a very simplified model, which, however, illustrates that possibly we are dealing with emission which consists of two components which may have very different origins. And also in this figure you can see the measurements from HES, these gray points, which I hope you can see my pointer, and these points corresponds to emission from each of the jets. So the LASO points, they correspond to the total emission from the system. So basically we have to sum up the HES contribution to check if the flux level are consistent between HES and LASO. And well, we can see that there is a nice agreement between these two instruments, and also that at the present moment HES cannot constrain existence of this additional component, which is also actually according to the results obtained with LASO, it has a different spatial origin. And here we can see this the significance map for the emission above 100 TeV detected with LASO, and it can be seen that it's somewhat offset from the system and potentially coincides with a nearby molecular cloud. But Rui was talking about this data in more detail recently, so I will not go into more detail here. And then let me kind of briefly discuss what we can learn from a quick inspection of the data. And looking at the significant maps obtained in radio and X-ray, we can see that the jets represent an essential feature for this system, and basically they propagate from small scales to this like tiny fraction of parsec to this 100 parsec scale, and essentially they transport very significant amount of energy. Using X-ray and TV data, we see consistent result that there is a kind of rebrightening of the jets approximately 10 parsec from the binary system, which most likely implies existence of a shock, which can be dubbed as the termination shock, or maybe it's a reclimation shock, where particles get accelerated and then they keep propagating in a coherent way further away from the systems. And since there is this generosity for synchronous emission between the strength of the magnetic field and electron energy, only using TV data we can robustly confirm existence of multi-TV electrons in this system. And also, again, since we're dealing with two independent channels, so synchronous emission and TV emission, we can better constrain the properties of the target, such as magnetic field strength. And again, we see a consistent picture that that electrons are accelerated to multi-TV energies at the innermost node in the jet. We also may see kind of evidence that there is acceleration of protons also occur in this system, which in principle we should expect, because we know that the jets are not electron positrons, but there are protons, and the conditions in the jets are suitable for diffusive shock acceleration. Therefore, we expect that at least a comparable fraction of dissipated energy is transferred to relativistic electrons. However, transferred to relativistic protons. However, relativistic protons do not meet sufficient target in the jet, and they can be deflected away and ejected into interstellar medium close to the microquasar. So kind of this makes it to be a powerful source of cosmic ray particles, but still we can see some emission if especially there is an enhanced target in the vicinity of the source. And let's look at the physical parameters of the system. So such as the jet power. So from radio observations, we know that the jet is powerful with approximate kinetic luminosity of 10 to 39 ergs per second. So from the X-ray observations, we can determine the distance from the compact object to the termination shock. From the lateral extension of the production region, we can estimate the jet opening angle, and it should approximately 10 degrees, and we can get a quite good estimate for the jet radius. And this basically obtained from the visual inspection of the X-ray images obtained from the source. Using these parameters, we can try to look into the parameters inside the jet. And for example, if we can estimate the jet ramp pressure once the jet passing through a shock, this jet ramp pressure is converted into gas pressure in the shocked material. And just using this rough estimate, we can see that the pressure in the jet is quite high, about 300 electrons per cubic centimeter. And we can look at equivalent magnetic field strength, and well, just by equating the magnetic field pressure to this parameter, we get that magnetic field can be up to 100 microgauss in the jet, but this should be considered as a strict upper limit for the magnetic field strength. And also we can think of energy density of photon fields, and as usual in these kind of extended sources, the background photons provide the dominant target, and as usual we have to account for cosmic wave microwave background. We'll have to account for different infrared photon fields, and probably we are dealing with a photon field which has like maybe like 5 eV per cubic centimeter energy density. We also know the mass loss rate of the jet, which was estimated at the level of 10 to minus 6 solar masses per year. And since we know the jet speed, we can think of typical density, which appears to be 10 to minus 4 protons per cubic centimeter. And we can, just for curiosity, we can look at, for example, at the sound speed in this plasma, which appears to be quite high, 10 to 9 centimeters. And finally, using these parameters, we can look at the parameters which determine non-thermal radiation from this system. Of course, the most important parameter is radiative cooling time, which for 10 microgauss magnetic field, we should expect cooling of TV electrons over a scale of 10 to 5 years. And also using the kind of some value for the magnetic field, we can estimate the typical electron energy which generates X-ray emission. And again, for 10 microgauss magnetic field, the 10 keV emission is generated by 100 TeV electrons. It's interesting to look at the inverse Compton emission on infrared photon fields. So for example, we took 100 Kelvin photon field, then 10 TeV photons are generated by 25 TeV electrons. And what is also important here, that since we're dealing with 100 TeV electrons in the jet, we can think not on cooling time, we can think on cooling length. So how far can these particles be affected along the jet? And we can, well, it's a kind of a very trivial estimate. However, I believe it shows an important feature that in fact particles can cool relatively efficiently in this 10 parsec jet, and therefore, if we want to model the emission from these jets, we have to consider models or kind of scenarios which describe the particle transport in the jet. And let me introduce here the kind of a very basic model which allow to describe this transport. Of course, one can go and make some hydro simulation. However, there are always uncertain about the initial setup, and these kind of simulation are still computationally very expensive, and still a role of simple, almost analytical models is quite important, and we can better understand many sources using this kind of approach. And if we want to formulate the simplest model that allow describing the transport of hydrogen particles in relativistic or mildly relativistic jets, we have to introduce several features. First of all, we have to postulate existence of accelerators in the jet. So basically, one has to define their position. One has to determine the spectrum which they produce, and there could be single acceleration site. There could be several acceleration sites. It depends on the detail of the modeling. So one has to assume some distribution of the speed in the jet. Again, well, this can be obtained with hydro simulation, but one can also consider this kind of some kind of simple analytic description of this parameter. Also, one has to describe the distribution of the magnetic field. Well, one can use, like, for example, if one determines the jet geometry and the speed, one can use a frozen condition to compute the strength of the magnetic field. There could still there is some freedom for selecting this parameter. And after that, one needs to account for adiabatic cooling and relative cooling in the jet, because, well, once the jet plasma propagates to a significant distance, it may undergo noticeable compression, which leads to adiabatic cooling. And well, here you can see a sketch from Pseudo-Sun's paper, in which explains how this kind of model works. And below you can see the standard transport equation, which relies on continuous loss approximation. And here we have energy time coordinate dependent injection. We have terms which describe the particle evolution. We have terms which describe particle advection, and also relative and adiabatic cooling. So this is basic equation which can be solved easily numerically. And in the simplest case, we just assume that there's a single acceleration site, and the data suggest that these acceleration site should be placed at the innermost node seen in X-ray, and it coincides with the onset of the X-ray emission. And this model was developed by Pseudo-Sun, and here you can see the spectral energy distribution from this from his paper, and it shows that this kind of model can explain the X-ray and TV emission. So that that time there was Hawk emission only, and one can test some basic parameters. In particular, here this plot shows the influence of the acceleration efficiency, and again we measure acceleration efficiency from this absolute accelerator. However, it's clear that this kind of model should not be applied to integral spectra from the sources, because they allow to study kind of morphological dependencies. And let me show you this figure again, and let me explain what is shown here and why this might be important for studying the emission from microquasar jets. Basically, well, here we can see that there is a kind of conic jet which propagates from the center of the system, and at a certain distance the particles get accelerated, and once they get accelerated, they start to interact with the magnetic and photon field, generating synchrotron and inverse Compton emission. And if we inject certain particle spectrum, once this plasma element moves downstream, the distribution in this particle distribution in this element gets cooled. So we're dealing with relatively complex distribution, spatial energy distribution of particles in the jet. And cooling of the particle most noticeably reflected in the maximum energy of the particles. So because we we always look at the particles which were injected certain amount of time earlier, and we do not really expect any kind of cooling break. So basically, all particles with different rates move towards low energies. And there is an important difference between the production of the TV inverse Compton emission and the X-ray synchrotron emission, because well, first of all, the inverse Compton target photons are nearly homogeneous across the entire jet. On the other hand, magnetic field may undergo certain fluctuations, and there could be regions of stronger magnetic fields, and these regions of stronger magnetic field, they does not significantly influence the inverse Compton emission, unless of course particles completely cools down in this region, but they can significantly enhance the synchrotron emission because the target is denser, and they also cause faster cooling of the particle, causing steepening of the spectrum, and therefore then we look at the X-ray emission from these jets. We can see much more detail, while for the gamma ray detectors, the size of the source is it's not exactly like PSF. We're dealing with a very large source, but it's much harder to reveal fine details using gamma ray instruments. And also, it's important to remember that the X-ray emission which we detect from the system is likely generated by electrons with higher energy than emission, which high energy, which than electrons which generate emission which is detected with gamma ray telescopes. So, and here at the bottom you can see again these estimates for the electron energy. So it means that we can use this approach to infer detailed information about the structure of the jet, most notably of the magnetic field in the jet, using X-ray observations. And well, as I said, X-ray observations have certain advantages comparing to the gamma ray observations. Like, first of all, the X-ray emission is likely generated by higher energy electrons than, for example, 10 TV gamma ray emission. X-ray telescopes have much better angular resolution, so they allow to reveal many detail which remain absolutely not accessible with gamma ray telescopes. And also, well, this source was observed for decades in with different X-ray instruments, and well, of course, the data which were obtained like 30 years ago with PROSAT, they do not match the quality of modern instruments, but also this system was observed with Chandra many years ago, and one can compare X-ray data obtained from different epochs, and well, and for example, Naomi Tsuji works on studying these aspects, these properties of the system. And So, well, I think this illustrates that if we want to develop kind of transport models, we first of all should look at the data obtained in the X-ray energy band. And here you can see, so I will first discuss this attempt to perform this kind of study for the WestJet. And this was this work by Kayama-san, and it was published in 2022. And here you can see the map, X-ray map from the WestJet, which was, and here the upper panel shows the soft X-ray emission, and bottom panel shows hard X-ray emission, and it can be seen that there is noticeable change of the surface brightness seen in the X-ray energy band. And the idea was to study the change of this emission brightness and photon index using transport model. So the entire region was divided in 12 slices, which are shown in the upper right corner. So the slices were kind of elongated, and they were aligned perpendicularly to the source axis, which kind of more or less the inner jet precession axis. And so one could get the spectra from these small regions. And here you can see the result. And the results show, so in the upper panel you can see the evolution of the photon index, and in the bottom panel you can see the evolution of the surface brightness. And we can see that there are some nodes in along the jet, and here you can see the labels which show how these nodes are dubbed. And so, well, we have the data, and we can apply the model similar to the one which I explained earlier. And here you can see the result. And basically, the model was designed to be quite basic. So one assumes constant propagation speed, and also one assumes that there is a basic strength of the magnetic field, and these figures show the simulation which describe the transfer brightening and softening of the spectrum caused by advection along the jet in a constant magnetic field, but also with additional enhancement at the approximate location of W2 node in the jet. And we have tested 3 different bulk speeds of the jet, and also 3 different enhancement of the magnetic field. And here the color shows the enhancement of the magnetic field in the node. And basically we considered 3 cases ranging between 20 and 60 microgausses, and the bulk speed was considered between 0.26 and 0.065 light speeds. And here you can see the evolution of the surface brightness and the photon index. So the middle panel is the evolution of the photon index, and the bottom panel is the change of the surface brightness, and it can be seen that in principle we can relatively comfortably explain the data if we assume that the jet is not that fast, so it's not it's slower than its initial speed, and also we can reproduce the increase in the surface brightening, and also we can see a consistent softening of the spectrum as shown here. Later, one extended a similar and performed a similar analysis in the East Jet, and here you can see the map of the source. So, and yeah, well, here there are nodes which are linked to the West Jet and this somewhat more elongated Eastern jet, and one applied a similar technique. So you can see in this figure, you can see both slices which were implemented in the West jet and slices which were introduced in the East jet. Again, the regions were selected to be perpendicular to this main axis of the system, even if the East jet apparently deflected in respect to this direction. Still, we used similarly orientated slices, and here you can see these 13 regions from which the X-ray spectrum was extracted, and here you can see a comparison of the parameters revealed from the Western jet and parameters revealed from the Eastern jet. So Western jet is in blue and Eastern jet is in red. And again, we can see here the change of the photon index and the change of the spectral brightness. In both cases, we see kind of consistent picture that away from the acceleration side, we see a gradual softening of the spectrum, and with the surface brightness, we see kind of more complex behavior. And we try to apply a similar model to this jet, and here you can see the result, the feeds from paper by Kayama-san, which is now submitted. And we can see that in case of Eastern jet, sorry, there's a typo, so it should be Eastern jet in the slide title. In case of Eastern jet, we can, using the same model as for the Western jet, even tuning the parameters, we cannot achieve a similar agreement. So basically, there is kind of inconsistency which we see in brightening of this increase in the surface brightness and absence of a noticeable softening of the spectrum. And it seems that this indicates on operation of reacceleration process in the Eastern jet. And basically, this brightening is caused not just by enhancement of magnetic field in this region, but rather by additional acceleration of particles in this region. And so here I got to my summary. So I have several minutes. So let me quickly go through these points. And again, so I would like to emphasize that by just using the very general analysis, we can see that X-ray emission detected from jets in SS433 is generated by almost ultra high energy electrons with energy about 100 TeV. cooling length of these electrons is comparable to the extension of bright X-ray bright regions seen from this system. Therefore, to describe the evolution and emission from this object, we have to consider models which account for the particle transport. And in principle, since especially ultra high energy electrons, they lose energy very easily, even a kind of relatively small enhancement of the magnetic field can significantly deform the electron spectrum. Therefore, we have to consider this transport model accounting for the data collected in the X-ray band, and especially that the X-ray instrument have perfect angular resolution, especially data which matches the extension of like degree extension of these of these jets, so we can get a lot of fine detail using X-ray observations. And using a model suggested by Sudo-san, Kayama-san has applied this model to study the distribution of the X-ray emission in the Western and Eastern jets. And while in the case of Western jet, the model agrees quite nicely with the surface brightness and spectral properties of the X-ray emission, and most likely these not seen in the Western jets are caused by enhancement of the magnetic field. The features seen in the Eastern jets are not consistent with this scenario where the emission is caused by enhanced magnetic field, and most likely we see an evidence for additional particle acceleration in the Eastern jets. And this may have important implication for interpreting the emission detected from these systems in X-ray and also in TV energy bands. Thank you very much.
Thanks, Dmitry. Thank you for a great talk. Questions? Paulo, do you want to take this over?
Sure, or we can do it together.
Okay.
Yeah.
So Susumu has a question.
Yeah. Hi, Mitya. Can you hear me?
Yes, I can hear
Yeah.
you.
Yeah. So this may be a question addressed not only to you, but also to the authors of the Hess paper on SS433, probably Brian and Laura, about the modeling in the Hess paper. So the modeling discussed in the Hess paper, which seems to provide a good description of the energy dependent morphology of the TeV mission. I don't think they show this kind of steepening in the X-ray band that is actually seen. Should I consider this due to what you actually said in X-rays? You look at much smaller, well, much more detailed spatial structure, and so for the modeling in the Hess, maybe it corresponds to a more average, spatially averaged kind of emission. Or maybe
Well,
yeah.
if I'm not mistaken, there
Mhm.
was no regions with enhanced magnetic field in the Hess paper. And well, if we will look here, we are talking about enhancement wells up to like 60 microgauss. So that's relatively strong. And I think in a Hess paper, one considered homogeneous magnetic field with 10-20 microgauss, something like this.
So maybe a question specifically to you. So in this kind of modeling, if you calculate the inverse Compton emission, would it reproduce the Hess measurements, or do you have to consider maybe larger emission integrated on larger scales?
Well, it should. Well, it's when we talk about this kind of prediction, it's just the question of ratio of magnetic field to energy density to photon field energy density. Since the magnetic fields more or less have the same strength, I don't think that there could be any noticeable problem in explaining TV emission. Of course, well, one should look at the morphological data, but in principle, I don't expect, and I think the speed which was favored by Hess modeling is about 0.05, 0.06. So I think it's largely consistent with these two modelings.
Okay, thanks.
Hi, just to clarify, and the size of the Hess paper, although I think the question is mostly answered, indeed, we did assume a constant magnetic field of 20 microgauss. And while it's true that we didn't show a plot of the spectral index steepening, what you find with the energy dependent morphology in the Hess result is essentially that, right? That like if we were to calculate such an index, we would also find that steepening, because we find that the position of the photons for different energies is shifting along the jet. So it's sort of the same result, different way to present it. We do actually compare, in terms of the presence of a magnetic field enhancement, we actually compared, at the time, the only publicly available image of both jets was not from XMM, but from ROSAT. So we compared the ROSAT image, and we found that there is sort of a small discrepancy at the position of E2 that could be explained with an enhancement of the magnetic field indeed. So this is very consistent with what Dmitry showed.
Yeah, okay,
Brian?
thanks.
Yeah.
Thanks.
Yeah, go ahead, Brian. Yeah, sorry.
Oh, yeah, okay. Hi, thanks, Mitya. Thanks again for the talk. I had a question about this reacceleration that you need to invoke. Have you put any thought into what that might be? I mean, would some type of adiabatic focusing be enough, or do you need to have another shock, or what do you think is happening?
Well, actually, it's quite an interesting question, because here we can see that the jet is deflected significantly comparing to its initial direction. So if there is kind of a oblique shock in there, the jet can remain supersonic, and there could be another termination shock. But one should really model this data. But what seems to be quite a robust result. So we don't see any. We see very considerable enhancement of the surface brightness, and if we even nearly try to reproduce it by enhancement of the magnetic field, then the emission photon index is overshoot the measured values very strongly. So I think we see an evidence for quite significant reacceleration of particles. So I would think that maybe another shock is a good candidate, and especially that the jet kind of abruptly stops, so it does not propagate much further. So yeah, I hope this answered your question.
Oh no, I think it's fascinating, of course. Do you think this is something we had a deeper, for example, is this something with CTA that we might see a second component appearing there as well? I think.
I think so. Yeah. There could be, well, with CTA or maybe with LUCT, which may have very good angular resolution around few dV. So I think this could be well, in general, this is an exciting source, and I'm sure that with CDA and other instruments, we will see a lot of new details.
Thanks, Mitya.
Yeah. Any other questions out there? If not, I have some. Okay, Evgeny, go ahead, Evgeny.
Thank you for your talk. You didn't say anything about the initial acceleration site, except that it should be somewhere upstream of any node. And I wonder whether you can tell us something about its possible location. And
Well,
actually, another question is, shouldn't we see it if it's out there?
Yes, we see it. It's clearly seen in the X-ray. Well, actually, it's even clearly seen in this ancient Rosat image. So well, it's basically just here at about 10 parsec. We clearly see it in X-ray data. We clearly see it in HES data. I think there are we are in a situation then we can just accept that there is kind of termination shock or reclamation shock in the jet which accelerate particles, and we do see its position. Well, even just look at this HES image. So if we look at highest energy emission, we see that there is kind of onset of this emission, and it coincides with the location of the innermost X-ray nodes. So I don't think that there are any reasonable doubts in
So it's
location.
not a question of doubts. It's a question of whether we can really hope to see that this is an acceleration site and not something else. I mean, for example, in nearby supernova remnants, we clearly see a very thin shell, very thin bright shell at the shock. If it's a termination shock, then is it a hope to see something similar at this distance or not?
Then you talk about supernova remnant. Well, here we are dealing with kind of system which to some extent more similar to pulsar nebula. So we have kind of a standing shock, and the plasma in the downstream still has significant bulk speed, and the particles are carried away. And well, what you say, well, like kind of thin shell, well, probably, well, just we see in HES data. Yes, well, we see very well localized emission above 10 TeV. I think it matches quite well what you expect to see.
Thank you.
Any other questions so far? I have some questions if not, but let's see if anybody else raises their hand first. Okay, no one there, so I'll take the prerogative then. So very interesting, Mitya. So I was wondering, so with a synchrotron lifetime of 10 to the 5 years, that's actually longer than the lifetime of SS433. Like some hydro simulations give like 10 to the 4, maybe 10 to the 5 years. So how do you explain such sharp features? And that's one thing that's always bothered me.
But it's 10 to 5 for one TeV electrons.
Yeah.
When we are talking about 100 TeV electrons, we get a significantly smaller, right? And then basically for the question is just we basically see emission produced by ultra high energy electrons, and they have much shorter cooling time. And
yeah, but even if like L synchrotron, even if it's 0.1 parsecs, that's still sharper, I think, than the features seen by Chandra or the knots that you showed.
well,
like
with
particular-
X-ray data, it's we not only see the kind of the transformation of the electron spectrum, we see the regions of enhanced magnetic field, and we can generate arbitrarily thin features. Even if the cooling time is very long, we just have kind of narrow layer of enhanced magnetic field, and it generates much more synchronous emission, and it appears as a bright, narrow, very thin feature. I think it should be.
No, I agree with that, but somehow though, it's not completely obvious how it works in practice, because you need a pretty big contrast. Maybe other people can say, but is that naturally expected to have such a strong contrast, or do you have sort of magnetic field generation in situ? So your picture is sort of the standard semi-homogeneous jet where things propagate down, but to me this looks like something extremely inhomogeneous, maybe with very strong magnetic field enhancement and trapping. What do you guys think? Anybody else too? Yeah.
There are no
Oh,
hydro people.
yeah. Anybody, or maybe, well, Brian, I don't know, or is Andre still here, Bikov, or yeah.
Yeah, I mean, I guess you're thinking the same, Paolo, as if there's in situ cosmic ray acceleration and it's self-amplifying the fields ahead of the shock.
Yeah.
Is back in the upstream. I mean, this is of course possible. Of course, the high polarization that was seen kind of challenges that to some
Yeah.
extent. But of course, it's not clear, of course, where exactly the shock is, I guess. So you could be seeing some smearing into upstream. I mean, we see the same thing in RxJ 1713, right? That you see the X-ray emission is quite sharp, and then you see the Hess emission is a bit more broad,
But-
going over it. So you still see these sharp transitions occurring, and how much of that is in the stream, and how much of that is, you know, in the post-shock region is not entirely clear. Yeah, I can't say much more than that. I mean,
Yeah.
the IXP results are really interesting in this regard because they're more in the case of supernova remnants, that they're more highly polarized than you would naively expect if you want this very strong nonlinear magnetic field amplification. So it does require a little bit more thinking, I think.
Yeah. Because and maybe John, a question for Mitya. Have you thought about the XP results, the polarization, the field orientation, and is that?
Oh, that's in another domain. Well, in principle, these should well we see it's kind of at high angle. So the at such large distance we the magnetic field carried by the jet should be almost all toroidal. So if there is a significant generation of the magnetic field, we can amplify the poloidal component, and probably this can be tested with polarization observations. But I have not been thinking about this possibility. That's an interesting direction indeed.
Yeah. Okay. All right. Yeah. So there's a lot. This is a data-rich object, so there are too many constraints. Maybe any other question? One other thing I was wondering about, if the field is 20 microgauss, in terms of the old sort of synchrotron models, is UB much bigger than URAD, or is it comparable? So that if you amplify the field, you'll also decrease the Compton flux. Is that?
Yeah, but I think we cannot. Well, we can amplify a magnetic field in some compact regions. So there would be like strongly non-homogeneous configuration, and then inverse Compton emission can be generated in the regions with weaker magnetic field, almost. So
Yeah.
it can be relatively little affected if we consider this kind of multi-zone configuration. And I think it's not feasible kind of to amplify magnetic field in the entire region homogeneously. So probably it should not be a big problem.
Okay. And one other random question: does anybody know? Are there new star observations? Are they relevant, or this cutoff is so sharp in X-rays that it might reveal a trace of some very high energy acceleration, or sort of at 30 kV? Is there an observation or anything? I should know this, but I don't.
I mean, there's Chandra, but I'm not sure about New Star. I don't know if Naomi or Kaya are online, or Julian.
Yeah, Naomi's there, but let's see. Yeah.
Yeah.
Yeah, we have new star data, but I don't think we see any cutoff.
Huh.
It's detected up to 20 kV for sure, but maybe it's difficult to detect 30 kV with new star because it's like stray light issue or background is very high.
Okay. But it's consistent with some rollover that starts at 10 kV, say, or?
I don't know. I need to check with Kaya or someone.
Okay.
Yeah.
Great, because there could be extra information from that. All right. And one other question. So, does someone remember from the lasso source is maybe is more consistent with the central object? Is that true? So that the jet and everything that's going on is not necessarily what's accelerating the highest energy cosmic rays. If there's a hadronic component, is that?
Well, the lasso shows energy dependent morphology. And if the data collected, let's say at the TV, like 10 TV, they are more or less consistent with the jet outflows. So there is no, at least striking discrepancy to the Hess morphology or Hawk data. If we look at the energy collected at higher energies, let's say starting from 100 TV, then the emission comes from a region which especially coincides with a molecular cloud nearby. So that's why one was thinking that the highest energy component is generated by ultra-relativistic protons, and it's kind of different from the emission seen with Hess and Hawk. And I think I have here somewhere figure which shows it's exclusively for above 100 TV data. So but the low energy data are consistent with these jets lobes. Yeah.
But could I just ask a bit more about
Go ahead,
that?
Andrew. Yeah. Oh, oops. I guess Andrew had his hand up. Let's see.
Okay, just quickly, because I want to fill on this. I mean, I saw, Mitya, that you focused on the jets, but now that Paolo's brought that up, that sort of triggered my attention. So there's nothing from the X-ray that sort of let's say corroborates that hadronic scenario from the center region?
But it's not the central region. Well, well, if you say the
Okay.
central region, I would think about the binary system. Lasso
Sorry, wrong
is a
word.
significant offset from the center of the source. Yeah.
Okay.
But well, probably Naomi is, well, if you're talking about the constraints from X-ray emission, which come from the emission of secondary pairs,
Yeah.
then probably we don't have any problem because these the emission is quite faint actually, and it's very extended that probably it's very hard to detect it with X-ray instrument. Although somehow one should consider a realistic model which describes the penetration of protons inside the cloud. And because if we look at this kind of morphology from Lasso, the X-ray morphology can be quite different, and there could be much narrow features. But I don't know if it was modeled, and but this is I think this is something very interesting to look.
Okay, thanks.
Yeah.
Great. And Enrico has his hand up. So go ahead, Enrico, if you want.
Hi. Yes, I have a very general question on this association of the highest energy emission with the cloud.
Yeah.
Okay. So,
Mute.
can you hear me?
Yes, I can hear you.
Okay. So, Lasso paper suggests a distance of 4.6 kiloparsec, while
From where?
Of SS433 from us, and while the uncertainty is pretty large, and Hess suggests 5.5 kiloparsecs. I was wondering if there is a net distance or evaluation between the cloud and SS433 itself, or how can we be sure that the cloud is actually consistent with the location of SS433 if there is such a huge uncertainty in the SS433 position?
Well, I think the answer is that if there is such a significant uncertainty in the position of SS433, we cannot exclude the cloud association. So it's, well, it's I think it's these arguments works one way around. So because of this uncertainty, we should keep in mind that this could be the right scenario. Yeah, but the point is that also, you know, like yeah, there are a lot of uncertainties here, and there was not even kind of detailed modeling of the cosmic ray proton transport from the system, because what you can see here, it's like oversimplified model which basically does not include any propagation model. So at the present moment, probably I would not worry about this kind of possible different distances. I don't know.
Yeah. Okay. No. Actually, my question was more oriented towards understanding if we have more observable to put the cloud close enough. I wasn't arguing about the possibility that is actually there. I was just wondering if we have more proof about it.
Well, I don't know, sorry.
Yeah, we can check. Okay, we're getting close to 10:30, so we should stop. We have one more question from Susumo, maybe. Thanks, Rico. Yeah.
Yeah, so related to what was all discussed now, I think this is what actually Paulo was trying to get to. But so at the moment, assuming that the last mission at high energies is hadronic, it's consistent with being accelerated at these the edge of the inner edge of these jets, the whatever, whether it's a term some recollimation shock or
Well,
do it. Yeah. Okay. I guess. Okay. And
the
maybe
point
it depends.
is the following, like protons can travel relatively easily, and basically we see the we don't see the protons, we see the target. And to answer your question, probably we don't have data, because if there is the kind of the central part and this kind of lobes, they kind of like say, I don't know, like 20 parsec apart. That's relatively small distance for ultra high energy protons. So, well, if we are talking about the source is probably 100,000 years old. And then the diffusion radius for these protons will be approximately 1 kiloparsec. So, and it means that they can easily create a more or less homogeneous density within, let's say, 100 parsec from the source, and we just see the regions of the enhanced target, and it doesn't matter from where they started, from the center of the system or from the kind of inner lobe, or from the very final termination region. I don't think that there is we have data to discriminate between these.
Okay. Thanks.
Sorry.
And maybe even though I said we should stop, the discussion reminded me of the discussion last time. If I take the total power you get in the electrons and radiation, then multiply by some inefficiency factor, like the electrons only get 5% of the energy and protons get the rest, do you have efficiency problems? How much power is
well,
accelerated particles?
Okay, again, it's a question.
Yeah.
For this target, we and to get this plot, one assumed, if I'm not mistaken, approximately 100 times more energy in protons. The real problem here is the spectral index, because, well, as you can see, these hard dashed blue line implies that either the injection spectrum is very hard, or the injection started recently, so only highest energy proton reach the cloud. From the point of the energy balance, we need more energy in protons, but it's not dramatic difference. So it's more or less consistent with what people expect in case of diffusive shock acceleration, like maybe 30, 100,000 times more in protons.
Okay. All right. Okay, that's great. So Mitya just had a qualifying exam for graduate school, I think, so he survived. So with that, let's thank Mitya and everybody for sticking around so long. And Rashmi, any final words, or are we restarting? Is this the last?
Yes. Thank you for attending. This is the last for this season, for this year, but we are going to resume again in January, February. So please stay tuned. And thank you, Mitya. That was really excellent. Please send us your talk and we'll post the recording. So all the best and
Thanks.
stay.
Thanks again. Yeah.
Bye.
Bye
Thank
bye.
you.